Uh, dear friends, uh, dear friends, let's start our today's seminar. Our speaker, Professor Dupay, and he will tell us about gauge theory and skein modules. Let's welcome.
Thank you. Thank you for the invitation to speak and for the interest in this work. And thank you all for showing up. So this work aimed to um, study scaling module from a physics perspective by relating it to quantum field theory. And I assume that the audience are mostly mathematicians. I will start with um, the math side of the story. Um, I assume that many of you are very familiar with skein modules, but still, let me start slowly. And if you find this is some part is too quick, please also ask questions and to slow me down. So the skein module is closely connected to the skein relation. And one of the most familiar skein relation is that of the Jones polynomial. So let me write it down. So this skein relation, um, not surprisingly, was originally found by Jones. That's one of the first thing that he did after defining the Jones polynomial. So I think the motivation for introducing this is that this plus another, oops, wrong color, another relation give a quick way to compute the Jones polynomial of any link in R3. So if I have any link, by applying these rules, I can find its Jones polynomial. So it's going to be a round polynomial in the variable q with integer coefficient. And this ring is actually already an example of a skein module, although it's a little bit simple, but this is a skein module associated with three sphere. So one can play similar game for more general three manifold. So if I take a three manifold, and let me emphasize that this is a three manifold by using subscript 3. Let's assume that this is connected, oriented. Then, if one apply the Jones skein relation for the Jones polynomial, in general, one cannot end up with a Laurent polynomial in Q, but instead, one end up with an element in the skein module associated with M3. So this skein module can be defined as first we look at linear combinations of isotropy class of oriented link in the three manifold. And again, when modeled out by the skein relations, so again, these two relations, then that define module over this ring, and that's known as the skein module. And it has a lot of generalizations. In particular, one can define this for any ribbon category. Let's denote it by C. One can similarly define a skein module with C being an input. And if C is temporally lib, then that gets back to the original skein module. So for this, probably I will write it without the subscripts. So this is the original Kaufman bracket skein module. And another example, which is more relevant for us, is when C is rep QG, with G being a Lie group. So it's let's assume it's connected, compact. Well, it's either a Lie group or algebraic group. Let's work with Lie groups. And then in this case, that also define a skein module labeled by G, and I will denote it as skein sub G of M3. And when G is SU2, this get back to the Kaufman bracket skein module. So therefore, this would be a natural generalization of the original skein module to general Lie groups. So any question at this point? So skein
Excuse me,
module.
I have one
Yes.
question. When we define a skein module, here the skein relations are, if this skein relation is the skein relation for Jones polynomial, right?
Yes.
Yes. Then
But,
could you remind me when which C gives this SKM?
So when C is a temporary lib category, so then it will give back to the original the Kaufman bracket skein module. So then, but here I'm writing the skein relation for Jones polynomial. So strictly speaking, I can only recover this with G being SU2. But as Kaufman bracket polynomial and Jones polynomial contain the same kind of information, actually for the skein module, they are also isomorphic. So SK would equal to SK SU2.
Thank you very much.
So also, I won't be terribly careful with SU versus SL. So in the world of skein modules, it's more common to use the notation for algebraic groups. But later we are going to relate to gauge theory. There, it's more common to use the compact gauge group. And they are related by complexification. So I will, in a sense, use this interchangeably. So further questions? Skein module has a lot of connection to physics. So it has connection with 1D systems because, well, it's here, it's given as a module over this ring. But in this talk, we are going to work with the field of fractions. So these are rational functions in Q with rational coefficients. Then this would be a vector space. So alternatively, this is the same as working with generic Q. And because it's a vector space, then there's an immediate connection with physics. So one can ask whether this can be the Hilbert space of a 1D quantum field theory, or equivalently, the quantum mechanics. So what makes this connection more immediate is that the skein module is, in a sense, a quantization of the character variety. And already the word quantization appeared, and it seems clear that there should be a way of regarding skein module as Hilbert space of some quantum mechanics. But if this is a symplectic space, then the situation will be way easier. One way to quantize a symplectic manifold is to consider some kind of a sigma model.
And which manifold will be symplectic, excuse me?
So here, it's not symplectic. I'm saying like in a hypothetical world where we have a symplectic manifold, then one can obtain its quantization via a sigma model. So, but this is not symplectic. In a sense, it's a shifted symplectic. So the connection to quantum field theory should be actually lifted to 2D, where the picture is that in the middle, one have actual sigma model. And now I can answer the question. The sigma model is the target of that is a character variety associated with Riemann surface. And one can take this to be the Heegard surface. Then this model has two boundary conditions. And then that's associated with two handle bodies. So
And
associated with
where do this handle bodies appear? So character varieties, why does it look like this?
Yeah. So one way to view this is as intersections of two Lagrangians in the character variety associated with the Riemann surface. So one have the free manifold M3 with some Higard decomposition cut along a Riemann surface.
Yes, I know
sigma.
that. I know that it appears for M3. So every M3. Okay. So we have a Higard decomposition. Okay. So you can just say, let's consider a Higard decomposition of M3.
Yeah, for Higard, in principle, it can be slightly more general, but of course, one can just consider Higard composition of M3. And then one gets two handle bodies on the two sides. I have denoted them as M3 plus, M3 minus. And then they give Lagrangians inside this space, which has a symplectic structure. So one can actually come up with a 2D A model. So it's a twisted version of the supersymmetric sigma model, such that one can argue that the Hilbert space is related to the skein module. So there is a cartoon of this kind, but it's actually not very precise. So in past work, we have studied a little bit from this 2D sigma model point of view, and then there's some confusions that I will mention shortly. But any further questions about the connection to 1D and 2D? So there's an obvious connection with, yes.
M3 plus and M3 minus, for them to be Lagrangian, they reside in then this time a six-dimensional space which has a symplectic structure. Is that the
Sorry,
or
M3 plus, so M3 plus and M3 minus, these are handle bodies, so they are three-dimensional with two-dimensional boundaries. So here, this would correspond to some boundary conditions of the sigma model, and then they are given by Lagrangians inside some bigger space. So the dimension of this can be arbitrarily large if G is sufficiently complicated, and or if sigma is of higher genus. But these are half-dimensional.
Okay, but do we have some sort of a bound depending on the genus of how high the dimension can get, and is that relevant?
Yeah. So
I would think it
so
would be.
the dimension can be computed. So it's well, if I remember correctly, this is basically dimension of G times at I think 2G minus 2 or something like this.
Okay, thank you.
More questions? So there is another connection, also pretty immediate, with 3D T-cravats or 3D Chern-Simons theories. Because, well, Jones polynomial famously has a connection with expectation value of Wilson lines in Chern-Simon theory. So therefore, one can ask, what's the connection between the skein module with Chern-Simon theory? So here we see some connection, the appearance of skein module on both sides, but the connection is not super clear. And finally, with 4D, n equals 4, a gauge theory. This is because skein module associated with three manifolds is, in a sense, a natural extension of one version of the geometric long length program. But one way to embed geometric long length to physics is to use 4D n equals 4 gauge theory. This is studied by Kaplan and Witten, and then Gukov and Witten, and with a lot of interesting follow-ups. Then one can ask, what's the actual connection between this theory with topological twist? So the entire Kaplan-Witten framework. So what's the connection between this gauge theoretic framework and skein module? So one perhaps would be hopeful that if one just look at the Hilbert space of the gauge theory, so the gauge theory would have a Hilbert space. It's a 4D gauge theory, so you can have a Hilbert space on 3 manifold. Maybe that's just the same.
And what is the Witten index?
Oh, I haven't explained that yet, but I will do so in 2 minutes. So one can ask whether they are just the same. But if one compute things on both sides, then one already realized that this at the face value cannot be the same. So what is this counter evidence? So here I've listed the dimension of the skein module. So recall that it's a vector space. So one can talk about its dimension. For the case that the 3 manifold is just a 3 torus. So then for a fixed tree, one have vector space. They are all finite dimensional. That's a general statement from the work of Cunningham, Jordan, and Safronov. And in particular, one can compute its dimension for basically all SLN and GLN. So here, for example, for SL2, one find it to be 9-dimensional. So this is due to the work of Corriga and Gilmer. And then for SL3, SL4, SL5, there's a sequence of nice numbers. On the physics side, one can also do some commutation. That's, in a sense, the dimension of this, but it's a graded dimension. So because it's a graded dimension, maybe you think that it need not equal to this. And indeed, if one compare, one find that for SL2, well, it differs by 1. So that's not much. For SL3, again, it differs by 1. Maybe at this point, one will guess that the difference is always 1. But here we see that this is way larger compared to the dimensional skein module. And this actually becomes smaller. And also, they are qualitatively different for GLN. So for GLN, the dimension of the skein module, it's well, always a positive number. But for Witten index, it can be 0 because it's a graded dimension. So, so this is a graded dimension of the Hilbert space associated with T3. So if one wants this relation to hold, then one needs some modification. So because, well, at the face value, they are not the same. What's slightly worse is that if one consider now going beyond T3, which is perhaps slightly too simple, but one consider sigma times S1. So sigma is a genus G Riemann surface times a circle. That's a 3-manifold. And then one can ask, what is the dimension? And on the skein side, there is a beautiful result.
So excuse me, for
Yes.
such things and for virtual knot theory, it's much better to consider invariance and even Jones invariance, which is valued not in numbers but in pictures. And I'm working on that, and I wonder whether pictures may have any physical meaning, so we can consider an infinite dimensional skein module. Where we have, well, at least we can say not pictures, but homotopy classes of curves. And what then? So can we have any physical counterpart? Because skein modules, well, I prefer to consider skein modules which are infinite dimensional and which have, yeah.
Yeah, that's an interesting question. So I've never thought about this. So of course, this space actually would always be infinite dimensional. So one can then ask how to represent those states geometrically. Maybe what you are proposing would be an answer to that question. But this space, from the physics side, is also somewhat complicated. So I'm not
I would
going
be
to
happy
be
to
able to say
understand
much.
how it may be related to physics.
Yeah, and at this moment, I cannot provide a good answer. So I will tell you later that the tricks that we use to understand this space, but we can only detect some part of it. So then after that, it will be finite dimensional. So more questions? Okay, so for SL2, so the original Kaufman bracket skein module associated with sigma times S1, this is 2 to the 2g plus 1 plus 2g minus 1. So this was this formula was first written down by Gilmer and Masbon, who argued that this would be a lower bound of the dimensional skein module. Later, Datcher and Wolf proved that this is actually the dimension. What's so spectacular about this formula? So this formula has some terms. So there is this kind of term, 2 to the 2g plus 1. And that's something that physicists like to see, because this is actually a Cartesian function of 2D TQFT. So basically, in this case, it's a Z2 gauge theory. But then there is a part that would worry you if you are a physicist. So this term is linear in G. In particular, it cannot be a partition function of nice 2D TQFT. So why is this worrisome? So this tells you that it would be somewhat difficult to use the twisted 4D n equals 4 gauge theory, because that theory with a topological twist is supposed to be topological. And the quantity that it's going to produce are also supposed to be topological. So in particular, it will be quite difficult to produce a dimension formula with this kind of linear term. So that's something one have to overcome to connect skein module with physics, like what's going on with this linear term. And we are going to later solve this puzzle. And in particular, we are going to generalize this to SL3. So there, we're going to derive a new formula. So wait a second.
Excuse me. What do I mean by a finite dimension? So if we have already some non-trivial homotopy or homology classes, we can draw lots of curves, lots of parallel curves just in this class, and we will have infinitely many additive generators. Hmm.
So for T3, so this is T3. Then, so what is this line generators? So they are given by inserting either you insert or not along this direction, along this direction, and along this direction, right? So that's 2 to the 3 equals to 8. But then there's a special one.
Well, excuse me, but already if you have a torus, so you can draw lots of longitudes, and additively, yes, and so it will be infinite dimensions. So you have one longitude, two longitudes, and
if
so
one
on.
draws 3, then by skein relation, that can be related to a linear combination of these 9. So here we have.
No, I don't understand. So, if we can, so we may say that it's somehow it's multiplicatively we have something finite dimensional, but additively it's not a finite dimensional.
If I add
No,
another
even
friend
over an annulus, even on over an annulus,
over
it's
annulus,
infinite.
it's infinite dimensional. But here we are looking at a compact 3 manifold, and then a theorem by Cunningham.
No, I don't understand.
Jordan and Sapranov.
No.
That's for compact 3 manifold. This as a vector space. This is a finite dimensional.
No. No. Just consider compact with a boundary. No.
Yeah,
Well,
with
yeah,
boundary, then it will be it's often
no.
infinite dimensional. But here we are considering this without boundary.
Yes, but without boundary, just on the torus.
Let's say the 3 torus.
Okay. Yeah, but in okay.
Yeah, for 2 torus, the skein algebra
Yes.
is infinite dimensional. But
Okay.
here we are looking at 3 manifold skein modules. So more questions?
Okay. Please finish writing the formula.
Yeah. Okay. Let me get the formula. So structurally, it's pretty similar to the previous one. So there is a part that looks like a partition function of a 2D TQFT. In particular, in this case, it's basically a partition function of Z3 gauge theory. So the more precise statement is that that's the number of Z3 flat connections on this three manifold. But then it again has some part that's non-TQFT-like. So here, before it's a linear, now it's a polynomial.
What is the last summand? Is it 8 or what?
Yeah, it's a delta. So this equals to either 1 or 0, equals 1 if tree equals 1, and equals
Okay.
0 if tree is not equal to 1.
Okay.
So it has this part that's still unusual from TQFT perspective. It cannot be partition function of any 2D TQFT, but that's a present already for the SL2 example. But then now it has an additional delta function. This is even more exotic. So whatever physics connection with physics we are going to come up with, it better explain first this problem, some mismatch between dimensional skein module and Witten index, and also explain why non-TQFT pieces like this can appear. So I was looking at this problem probably more than 5 years ago when first learning about this formula from Gregor Masmon's talk. At that moment, I had some vague understanding of how to do this, but I can never fully get the connection with physics. But only recently I managed to put different pieces together, and now I think the story is, at least on the physics side, it's somewhat complete, but well, there are still some interesting questions and puzzles. So we're going to solve this in several steps. So this consists of 3 steps.
So by problem, you mean counting this dimension?
Problem means that how to reconcile this formula with gauge theory, namely Kapusin-Witten's approach. Or like just ask like what is the connection between skein module and any Hilbert space of any quantum field theory? Like what's the actual statement?
Okay.
Yeah, and that's actually going to be the first piece in understand this puzzle. So like first, we want to find some relation between a skein module with the Hilbert space of the gauge theory. But instead of stating that they are equal, the proposal is that there is embedding. Technically speaking, it's a dual of the Hilbert space. And this itself alone does not allow computation of those kind to do computation when use a certain deformation of the n equals 4 theory. That would allow us to do some computation. So this will be explained later. But then for this deformation, there are going to be certain defects known as cosmic strings. Which would explain, so all the three pieces combined, the claim is that they will explain these puzzles. In particular, this gauge theory will appear. The Z3, Z2 gauge theory will appear as a deformation of the quantum field theory. And the cosmic strings would explain these non-T-gravity pieces. So the outline for the remainder of this talk is to go through these three steps. So do I understand correctly that the total duration is supposed to be 1 hour and a half?
Yes, it's an hour and a half.
Yeah, okay, that's reassuring. Okay, so this is an illustration of the proposed embedding. So what is this picture? So one have the 4D, oops. And equals the fourth theory, perhaps with topological twists, three manifold. So that has a Hilbert space. One can view this as a 1D quantum mechanics with a Hilbert space. Now labeled by M3. So I have drawn this quantum mechanics. So low, like at lower part, X is in a sense the quantum mechanics time. So this is where the quantum mechanics live. And if I'm at a given point, I pick a point, then at that point, there's going to be a Hilbert space. So to propose to get a state in that Hilbert space, then what I can do is to pick some initial condition. And now I need to describe that initial condition. But fortunately, this the right boundary condition is already described by Witten. So in this work, Fibering and Knots, this kind of boundary condition has been studied. So on this side, there is a special boundary condition. And that boundary condition also allow insertion of links. So one can insert some Wilson lines. Those are going to be some links with components colored by representations of the gauge group. And this configuration, this boundary condition, if one propagates this, then one can get a state. So in other words, given a link L, then one can get a state in the Hilbert space. But because, well, this is a boundary condition, the state that one gets is usually not normalizable. So it's better to regard this as elements of the dual of the Hilbert space. So for any such link, one can get a state. And then one can just consider the collection of all such link, and then define the span of that. As we'll use this to carve out a subspace of the Hilbert space of the quantum field theory. And the hypothesis or conjecture is that this is exactly an embedding of the skein module. So why is this reasonable? So one thing that is quite suggestive is that here there are equivalence relations. So for different L and L tilde, they can give rise to the same states. But these are exactly the skein relations. So therefore, this seems to be a very natural proposal. So lately, this proposal is not terribly useful because the Hilbert space can be quite complicated. So given any three manifold, it's a difficult task to understand the Hilbert space of the quantum field theory on that three manifold. But what one can do is to pick certain states psi in the Hilbert space and then pair it with the state from these links L. And these are going to give function or functionals on skein classes. And with some reasonable assumption, one can argue that one can always separate skein classes in this way. So this is some test state. And one can pair this with a state from a link. And then for a different link, one get a number. So, and then it will be guaranteed to be the same on the same skein class. So this is a functional skein classes. And if it indeed separate skein classes, then one just need to come up with enough test states to come up test states that are linearly independent. And the number of such test states would then give rise to the dimension of the skein module. So still, this seems somewhat difficult because, well, what kind of test states that we are going to use?
I can't understand. Which states do you mean? Which states?
You mean the psi here? Is that the question
No,
about
I
psi?
don't understand what you are saying. Which states?
Test states. So these are
okay.
states in the Hilbert space.
Yeah.
So for any such state, one can pair that with those states given by a link. And one can use this to separate a skein classes. So if one can use any states, all states in the Hilbert space, then that would be really good. But as mentioned, we don't completely understand this Hilbert space. So what should we do? So the next ingredient is a deformation. So the idea is that for the 4D n equals 4 theory, there's a way to turn on deformation so that it's a 4D n equals 1. So it's a break some amount of supersymmetry. But this theory is easier to understand. So if one perform this procedure known as the RG flow, so physically this is about zooming out, looking at this theory at low energy. Then this will be a collection of IR phases. So what is this mathematically? One way to think about it is that there is a Hilbert space that one start with, but after the deformation, one have a direct sum of IR Hilbert spaces. And these two spaces may not be exactly equal, but there can be maps of with some nice property between them. So here we are using a particular deformation so that this collection is also very nice. So they are labeled by lambda. So this is a conjugacy class of SL2 triples in G, well, rather it's a complexification. And this is the same as Neopolitan orbits. In G, the algebra. So what's going on is that there's this space that is rather complicated, but then one can deform it so that it become something that can be understood. So here already we understand what is the label. That's just country classes of SL2 triples or Neopolitan orbits. And these are familiar objects for representation theorists. And then we just need to understand this for individual lambda. So to have some concrete example, let's look at this table. So what is going on here? So this is about the case where G, the complexification is SL n. Oops. And that's the same as the n here. So here we have SL2, 3, and 4. And lambda, in this case, will just be partition of n. So for n equals to 2, there are two partitions, either just 2 or 2 equals to 1 plus 1. So for n equals 3, there are three partitions, 3, 2 plus 1, and 1 plus 1 plus 1. And for n equals 4, there are now 5 partitions. So if I take the SU2 gauge theory. Now, in the infrared, now I have two phases labeled by these two partitions. And I have an infrared gauge group. I will denote it as G lambda. So this is IR gauge group. Oh, so this is slightly confusing, but here it's none of this. Well, let me just tell you the connection between G lambda and those things in the table. So C lambda will be the group of will be the component group. So in the table, you see that for n equals to 2, in one case, one have a Z2. And in fact, there, that's already the IR gauge group. So the infrared dynamics of this is just a Z2 gauge theory. And that's something that we really want to see, because recall that there is a piece that looks like 2 to the 2G plus 1. And this is the way to get it. So you have a Z2 gauge theory. And the partition function of that is going to count a number of flat connections on your 3 manifold. And for sigma times S1, this is what you get. So, so here I will just write G lambda equals Z2. So in this case, G lambda equals to just SU2. So the gauge group is not broken. And that SU2 is actually the same as this K lambda 0. And that seems to be not a simplification, because we started with n equals 4 theory with SU2 gauge group. Now we get n equals 1 theory with SU2 gauge group. And like, why is this simpler than the previous question? So what's simpler is that in this theory, there's a special physics phenomenon. Well, it's not really special. It happened for any simple G, known as confinement. What this means is that at infrared, the Hilbert space actually just it's just C2. It's a 2-dimensional vector space. So the theory has no dynamical degree of freedom. So the Hilbert space is really just a ground state, and then there is some ground state degeneracy. So one picture for this is that it's a ground state, and then there are, in a sense, like 2 bosonic states. So there can be some high energy states, but there is a gap. And that's what confinement actually means. So in real life, what's happening is that although gluons are supposed to be massless, but in the QCD spectrum, we don't see free gluons. Everything has a mass, so there is an energy gap. And here it's the same. There's an energy gap, so at low enough energy, we only see the ground states. And now, with some assumption, we can just work with the sum of these two phases and ask what's their contribution to a skein module. It turns out that all the vacuum states here, so in this case, so H lambda equals to 2, that's 2G, sorry, 2 to the 2G plus 1 dimensional space. And any of these, if we use this as a test vector, test state, those can separate some skein classes. Now here, there are two states. Let me denote it by this. But it turns out that any L, they pair the same with these two states. So these two states are inseparable by these skein classes, and they cannot be used to separate skein classes. So therefore, one gets, now if I take G equals 1, this is exactly the 8. So when G equals 1, this is 8, plus a 1 equals 9 decomposition. So the 8 comes from this phase, where the vacuum states are flat connections, and now on T2, sorry, T3. So these are flat Z2 connections on T3. But then this comes from this funny phenomenon, confinement. And I can even say more, like why this would lead to the previous state. But maybe let's not go too much further into this, but just a remark that it's exactly this decomposition. And in particular, one can argue that this kind of interesting looking states is needed because of confinement. So then one can compare this with index. So here, I see that for this phase with Z2 gauge theory, the dimensional skein module agree with Witten index. But for this, the Witten index know about both states, but the skein module only know about one of them. And that's a missing one. So for skein it's 9, for index is 10. And sometimes this is known as 10 versus 9 paradox. And that's, in a sense, a solution to this paradox. And this comparison can be done in for any n, because, well, in the end, it's just boiled down, writing down the partition of n, and then there is a physics question that one can translate into a concrete math algorithm to determine those numbers. And so here, for n equals to 3, there are 3 phases, and their contribution to index is for this one, this would be a Z3 gauge theory. the contribution to both is 27. For this, that would be a SU3 gauge theory with confinement. So in the infrared, one don't see the gluons. So if you have really low energy, you will not be able to see that it's actually SU2 gauge theory. And the vacuum now has 3 states, but again, only skein module only see one of them. In the middle, there is a phase where the infrared physics is described by U1 gauge theory. So it's like QED, but without the electron. The Maxwell theory. And the width index equals 0. But I still contribute to skein module. So here you see that this across the 3 columns, only one matches. But if you add the number together, they just differ by 1. So this is a 30 versus 29. But in fact, across the 3 phases, only 1 are actually having the same contribution to the skein module and the index. So one can do this analysis for arbitrary n, but it's simple to reproduce. This formula. So here, one sum over partitions of n, because, well, that's the phases. And then the summand is GCD of lambda cubed. So GCD lambda means, well, lambda is a collection of numbers that sum up to n. And then GCD of lambda is just the GCD of those numbers. And then to the 3rd power, you add them up together. That's the dimension of the skein module. And this agree and reproduce these results by Cunningham, Jordan, and Vazirani. And one can do this also for GLN. So for GL, one simply remove the 3rd power. Okay, so this by itself would explain the T3 situation, but we are still not accounting for this linear term that is non-T-Crafty-like. So to probe T-Crafty behavior, one need to look at a family of 3 manifolds. And in particular, we want to look at this. And then this has a genus, and whether it's a T-Crafty or not will have different behavior when we increase the genus. So the next ingredient is this. That's the cosmic string. So what's going on? So if one wants to consider this being the 3 manifold, we also have time. So if I consider the 4D theory on the entire thing, sigma cross S1 plus R. So this is, in a sense, time. And one want to deform this from n equals 4 to n equals 1. So what happens is that the deformation parameter is holomorphic differential on sigma. So it's not just a number, it's in fact certain form. And in particular, one can choose one such that it's parameterized by a holomorphic differential. Sigma. And in particular, you will have 2g minus g as zeros. So that sounds somewhat problematic because we want to turn on the deformation. But if g equals 1, then we can actually turn this on. But if g is larger than 1, then it has some zeros. Having zeros means that I'm having my Riemann surface. So I can turn on the deformation at a generic place, but then there are points where the deformation is not turned on. Therefore, one cannot directly go to the infrared because there are going to be these places where there can be some massless degree of freedom. And those are two-dimensional because they are points here, but they stretch along the S1 and the time direction. So they are string-like, and those are sometimes referred to as cosmic strings. So then we need to understand what's going on with the cosmic strings. So this is an illustration of the string. So I'm drawing the time direction. So this is a time direction. And well, so there's a S1, but that's not exactly the same S1. So that S1 is suppressed. So I'm only drawing the string as a one-dimensional object. But in the radial direction, if one is far enough, then one can have internal confinement if there's a gauge group that can be confined. But then on the string, there can be a massless degree of freedom. So that's in the beginning sounds somewhat hard to deal with. So what this means is that, well, before for this Hilbert space, one complaint is that it's infinite dimensional and hard to study. And we want to talk about the IR Hilbert space. But now, with these cosmic strings, this can still be infinite dimensional. So then what can we do? But luckily, so those degree of freedoms are localized on the string. So therefore, one can find a way to figure out this coupled system, how the bulk is coupled to the string. And if one reduce on this meridian circle, so this is this S1 that gradually shrink. So if one reduce along it, then one have the following system. So the bulk 4D theory now becomes 3D. And at low energy, it actually becomes the transaminant theory with gauge group G. And then there is some massless degree of freedom, but one can argue physically that these are just some boundary fermions. One can either view them as boundary fermion, boundary-free fermions, or WW models. So those are related by Bostonization, so it's not a big difference. So therefore, the coupling between the boundary and the bulk is just modeled on the coupling between transaminase theory and the boundary fermions. And then we know how Wilson lines in transaminase theory acts on the Hilbert space of the WW model. The Wilson lines in the bulk theory now acts on this, and that would from that one can actually still manage to get information about skein modules. So so what's the way to do this? So basically, what's going on is that let's again take G to be SU2. So there are two phases. So for this one, there are no interesting bulk operators. But for this one, the bulk operators are going to be labeled by representations. Let me use mu. So this is labeled by, let's say, irreducible representations. And it can act on the string Hilbert space. And one need to count Wilson lines mod this action. And that turned out to be roughly the same as counting Wilson lines up to what I would call central symmetry. So the center of the gauge group, in this case a Z2, would represent the symmetry. And two Wilson lines turn out to act in the same way if the difference is by elements in the center. So this is roughly because the boundary fermions, they are charged in the adjoint representation. So therefore, they cannot see the center. So here, this is for genus G, what's going on is that the transaminase theory has gauge group SU2, but it also has a level. The level is 4 times 2G minus 2. So for G equals 1, and the level is just 0. And then there are no interesting Wilson lines. So therefore, there is a single state. And for G equals to 2, I'm realizing that I'm having maybe additional. Yeah, so it's 4G minus 4, so it's 2 times 2G minus 2. So when G equals to 2, what's happening is that, well, so those are the relevant Wilson lines. But the Z2 symmetry acts in this way. So it would relate these two blue dots and relate these two orange dots and fix this blue dot in the middle. So this is SU2 level 4. It has 5 non-trivial the Wilson lines or integrable representations, irreducible representations. So I would write 5 lines but there's this identification. After that, there are going to be these 3 lines. So I'm also coloring this in some way, but let's first ignore that. So therefore, in this case, this would contribute, as opposed to 1, it will contribute to 3. And if one work this out, the contribution can be exactly fine to be 2g minus 1. And that's the linear term. That's from counting Wilson lines in transaction theory, or equivalently working with either quantum group or a representation of the loop group, and look at certain representations and count them in some way. So this is summary of contributions, but this is also supposed to explain the difference between blue dots and orange dots, but I don't think there is enough time for it, so let me skip this. But from here, you see some actually Langlands duality. So SL2 and PSL2, they turn out to give the same answer. So this is SU3. And this is the well alcove for SU3 at certain level. Now, the Z3 center symmetry acts by rotating this triangle by 2 pi over 3. And the fundamental domain of that action is this kite-shaped region. So for different level, it's of different size. And then one again counts number of points inside this. And then that's exactly this 3 times 2g plus 1 times g minus 1 plus 1 plus delta g comma 1. So this is because, so the counting is actually slightly different, because now there are 2 relevant faces. So one has to first count everything, and then for weights on the boundary, one needs to count again. So if one do this, one gets this expression. And that, together with the other part, is from gauge, Z3 gauge theory. So 3 to 2g plus 1. That's the prediction for the dimensional skein module for SU3 sigma times S1. So there are a lot of things that can be computed from the physics side. So let's, for example, look at Langlands duality. So those are examples where Langlands duality work. So this is SL2, SL3. This is for D4. For D4, so these are dual pairs. And the SO is supposed to be self-dual. This is a semi-spin group related to the SO by triality, and also supposed to be, well, basically self-dual. And then you can look at those formula, and then they turn out to be equal. And there is actual refinement. So that's why there are blue and red colored things. And those are also, with this refinement, they're also identical. But there are also cases where Langlands duality does not seem to hold. So here, this is a dual pair, spin 5, and that's the same as SP2 versus SO5. So if one compute this on the two sides, then here there's a mismatch of 7. And so why is this happening? There can be different explanations. One is that, well, this is physics computation and it involves some hypotheses. Maybe some of the hypotheses are not valid in these cases. But I'm intent to believe that this is actually a meaningful difference because from physics, one would argue that Lagrange duality would not necessarily hold. It only holds if one also add two operators. So in particular, this mismatch can be kind of explained by adding so-called toothed operators. So therefore, the prediction from physics is that when the skein modules themselves are not necessarily solvable, instead, one need to work with certain enriched skein modules, we will also add tooth operators. So in addition to the Wilson operators. So those are more examples where the Lagrange duality seem to fail, and that can also be rescued by adding the tooth operators. So more examples of this kind. And I think I'm out of time, but let me just show this last figure. So this is supposed to illustrate connection with geometry of the model space of Higgs bundles. So, well, there is some, so here, one can count the number of components, and then one can reproduce the result by Gilbert-Masburn and Daphne-Wolf. So maybe let me stop here.
Thank you very much for interesting talk. Are there any questions or comments? Yeah, actually, oh, sorry, do you have any questions? Thank you. I think if there is some question, then you may contact with Professor Dupuy by email, I guess. Thank you very much for interesting talk. Thank you very much.
Yeah, thank you for the invitation and for sticking around.